Section 7.2. 7.2 is on natural logarithms and exponential functions, and we are going to take derivatives and we're going to integrate. So you have to read through the section to get all the rules under control. So I'm just going to assume that you've read this, and we're going to take derivatives. Now, according to my chain rule, the derivative of the natural log function is 1 over the junk. Then you have to multiply times the derivative of the junk, which is 4, so we end up with the derivative of 1 over x. Part B is actually a product rule. So its derivative is going to be the first times the derivative of the second, which is 1 over x, plus the second times the derivative of the first. Simplifying this, I would get 1 plus the natural log of x. All right, part C. Y is equal to the natural log of the secant of x. So the derivative of the natural log is 1 over the secant of x. But then we have to take the derivative of the secant of x, which is the secant of x times the tangent of x. And the secant of x's are going to cancel, so the derivative is the tangent of x. Part D, we're going to use a quotient rule on this one. With the chain rule embedded inside it. So it is the bottom. The derivative of the top, that would be 1 over x squared times the derivative of the junk minus the top times the derivative of the bottom, all over the bottom squared. If we clean that up, we get 2x minus 2x, the natural log of x squared, over x to the fourth, which would clean up just a little more. I could cancel an x out. 2 minus 2 natural log of x squared over x cubed. The book takes it one step further and says, remember the rule for logarithms with exponents? You can pull the square down in front, and so it finally looks like that. Either answer is sufficient for me unless the directions say otherwise. Okay, example 2 is integrating. So we're going to integrate from 0 to 4 of x over x squared plus 9 dx. Now, since we're talking about the natural log section, this is going to be a u du, and you have to pick it to meet the requirements of a natural log, which means the bottom needs to be the u, and then du would be 2x dx. So you look over there and you say, all right, I've got the 1 over u, but I need a 2x dx, and I only have an x dx. So I need to stick a 2 inside the integral and a 1/2 in front. And then this turns into 1 over u du. Now remember the change of variables here. When x is 4, u would be 4 squared plus 9, or 16 plus 9 is 25. When x is 0, u would be 0 squared plus 9, or 9. So my values are going to be 25 on top and 9 on the bottom. So this is 1/2. The integral of 1 over u du is the natural log of the absolute value of u, which turns into 1/2 the natural log of 25 minus the natural log of 9, which, remember, subtraction when you're doing logarithms turns into division, and a number in front of a natural log is really an exponent, so it's 25 ninths to the 1/2, which means square root. So I end up with 5 over 3. There's a lot of information on the exponential functions with the e's. Make sure you read through that material as well. But we're going to example 3, which says, what is the derivative of 3e to the 2x minus 4e to the x plus e to the negative 3x. So according to your derivative rules, that 3 is just going to hang out there. The derivative of e to the junk is e to the junk times the derivative of the junk. Another e to the junk. The derivative of the junk in this case is just 1. And then here we get e to the negative 3x times the negative 3. If we clean this mess up, we have this. And that's it. It's stuck that way. That's the best you can do with that one. Part B wants us to take the derivative of e to the t over e to the 2t minus 1. Be careful when you're working with other letters besides x, because you get stuck in that x mode and you'll mess this one up. It has all t's in it. So this is a quotient rule, so it's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom, and that's going to be e to the 2t minus 1 times 2, all over the bottom squared. So if we clean this up a little bit and distribute, the e to the, oh, this is interesting. I want to be able to fit part C on here, so I'm trying to see how to squeeze it. Let's see. This is going to be, when you multiply bases, you add exponents. Here you've got a 2 and a negative sign to distribute. Yes, that's correct. No, something's not right. Let me see. Oh, minus plus 2 e to the t, all over the bottom squared. Collecting my like terms, I end up with oh, no, there's a big mistake here. Minus the bottom has to do the top minus the top times the derivative of the bottom. This is just, this shouldn't be here. There, e to the 2t times 2. So now when I distribute this, this is not even part of the problem. This is gone. So this piece is not even here. I knew it looked too long. All right, so I get negative e to the 3t minus e to the t all over e to the 2t minus 1 quantity squared. The book's answer, they factored a minus out of the top and left it out in front, which sometimes you don't see that negative sign because they lined it up with the division line. So be very careful there. Sorry about this big mess I made out of this. Part C. This derivative is going to be e, taking the derivative of e to the cosine of pi x, and then we're going to evaluate it at x equals 1/2. Okay, so the derivative of e to the junk is e to the junk. But then the derivative of the junk, derivative of the cosine, is negative sine of pi x. But then the derivative of pi x is pi. Now if I stick a half in there, I'm doing the cosine of pi over 2 on top. And then we have a negative, I'll put it out in front, and a pi. I should put that in front too, but there's no room. And the sine of pi over 2. So negative pi. The cosine of pi over 2 is 0, so that's e to the 0. The sine of pi over 2 is 1. E to the 0 is 1, so I get negative pi for an answer.